Hello again. This is Math 2115 coming to you from the College of DuPage. The title of this lecture is Mathematical Probability and Expected Value. Please, again, I encourage you to be an active listener while watching this video. In 1933, the Russian mathematician Kolmogorov provided a theoretical foundation for a far-reaching theory of probability. And so here is axioms. And while reading these, you should recall from previous discussions in this class that a sample space is a set of all outcomes of a random process or experiment, and that an event is a subset of a sample space. Here are his axioms. So we start with let S be a sample space. A probability function P, and this is a function just like in your other math classes. For every input, there's only one output. So a probability function P from the set of all elements in S to the set of real numbers satisfies the following three axioms. For all events A, B in S, those are subsets of the sample space, P of A is a number between 0 and 1. The impossible event is 0 and the sure event is 1, and everything else is a number between. Number 2, the probability of the null set, which is a subset of the sample space, is equal to 0, and the probability of the entire sample space is 1. Something must happen. Number 3, if A and B are disjoint, that is, they don't intersect except their intersection is the null set, then the probability of the union of A and B is the probability of A union B is the probability of A plus the probability of B. Let's begin applying that with this little problem. Suppose that A and B are events in a sample space S. If A and B are disjoint, could the probability of A equal 0.6 and the probability of B equal 0.8? And the answer to that is no, because since they're disjoint, the probability of A union the probability of B has to be the probability of A plus the probability of B, and that would be 1.4. But 1.4 is bigger than 1, so that would violate the probability axiom 1. Let's continue talking about some consequences of his axioms. The probability of the complement of an event. Suppose that A is an event in a sample space S. We're to deduce or prove that the probability of the complement of A is equal to 1 minus the probability of A. So here's the proof. Certainly A intersect A's complement is equal to the null set, and A union A's complement is equal to S. Thus S is a disjoint union of A and A complement. So the probability of A union A complement is the probability of A plus the probability of A complement, but that is the probability of S, which is equal to 1. So we're going to use algebra here, and we're going to subtract probability of A from both sides. So this is one side, this is another. So when we subtract that, we get the probability of A's complement is equal to 1 minus the probability of A. Often, this theorem that we just proved is useful. So if A is any event in a sample space S, then the probability of A's complement is equal to 1 minus the probability of A. Now, it is useful for us to check to make sure that these axioms are consistent with the results that we obtained earlier using the equal probability formula. Let's see that that's the case. Let S be a finite sample space with outcomes A1 through AN. It is clear that all the singleton sets are mutually disjoint because these are different elements. These are different outcomes. So they're mutually disjoint, and their union adds up to S because of the very structure. Since the probability of S equal 1, probability axiom 3 can be applied multiple times to obtain the probability of A1 singleton set union A2 singleton set union all the way up to A in Singleton sets is the summation from k equal 1 to n of the probability of A k. And that equals 1 because that's the whole sample space. If in addition, by assumption, all the outcomes are equally likely, there exists a positive number c such that all of them are equal to c. Hence, 1 is equal to the summation of c's, and that means we're adding c to itself n times, so that's n times c, so c is equal to 1 over n. It follows that if A is any event with outcomes A1, AI sub 1, AI sub 2, AI sub 3, up to A psi sub n, and we're taking any event here, and the probability is going to be the summation of those probabilities. Each of them is 1 over n, and we add m of them to give us m over n, and that's the number n set A divided by the number n set S, which is the result given by the equally likely probability theorem. Let's now consider the probability of a general union of two events. And for the proof, we're going to follow the steps that are outlined in A and B, but this is the theorem we're proving. If S is any sample space and A and B are any events in S, they're not necessarily disjoint or mutually exclusive. Then, the probability of A union B is equal to the probability of A plus the probability of B minus the probability of A intersect B. Now notice that we already know that this is true if the two sets don't intersect, because then they're disjoint. We learned, one of the axioms was, the probability of A union B is equal to the probability of A plus the probability of B, and we know that this probability is 0 by another axiom. So this is definitely true if the two events don't overlap, if they are disjoint. But we have to prove what happens if they're not disjoint. So the proof is going to involve us doing two steps. The first one is, suppose that A and B are any sets in the sample space S. We're going to A, show that A union B is a disjoint union of the following sets: A minus A intersect B, and B minus A intersect B, and A intersect B. So there's three sets that are union, and they make up A union B. Now if we look down at this picture, it really is obvious that that's the case, because A union B would be everything inside of the two circles. This is one of the sets. That's everything in A that's not in A intersect B. This is everything that's in A intersect B, and this is everything that's B minus A intersect B. Now we go through an argument here showing that that is equal, but I'm going to also suggest you could just appear to the diagram and conclude that yes, that is the case. And then B, so we've shown part A, or at least discussed part A. For B, show for any two events, U and V, in the sample space, if U is contained in V, then the probability of V minus U is the probability of V minus the probability of U. And the theorem will follow from this. Okay, so let's skip ahead to proving B. So in B, we know that the probability of A union B is the sum of the probabilities of these three sets, because we proved that in A that these equal A union B. So this is the probability of A minus A intersect B. This is the probability of B minus A intersect B1, or B rather, and this is the probability of A intersect B. But now, this result that we talked about here, the probability of V minus U is equal to the probability of V minus the probability of U. I would ask you to consider proving that as an exercise. Then is equal to the probability of A minus that probability. This one is the probability of B minus that probability. And this is the probability of A intersect B. But notice that this is the positive, that is a negative. They cancel out, and we have the result that we wanted to prove simply by algebra. Now you still have this issue, and you should go back and work on that problem. So So now you see we have a formula that allows us to compute the probability of a general union of two events. So here's a problem for us to work. Suppose a card is chosen at random from an ordinary 52 card deck. What's the probability that the card is a face card, Jack, King, or King, Jack, Queen, or King, or is from one of the red suits, hearts, or diamonds? So now these are not disjoint sets, because a Jack could be a Jack of hearts, for example. So let A be the event that the chosen card is a face card, and let B be the event that is from one of the two red suits. The event that the card is a face card or is from one of the two red suits is A union B. Now the probability of A is the number in A is 12, and that's 12 out of 52, so the probability of A is 12 over 52. Similarly, the probability of B is 26 over 52. And finally, the number in A intersect B is 6, because there are 3 face cards in hearts and another 3 in diamonds. And so the probability of A union B is 6 over 52. So from the theorem that we just proved, the probability of A union B is equal to the probability of A plus the probability of B minus the probability of A intersect B. We substitute all the values we calculated in, and we get 32 over 52, or 16 over 26, and that ends up being 61.5%. Thus, the probability that the chosen card is a face card or is from one of the red suits is approximately 61.5%. We now introduce the concept of expected value. People who regularly buy lottery tickets often justify the practice by saying that even though they know that on average they will lose money, they are hoping for one significant gain, after which they believe they will quit playing. Unfortunately, when people who have lost money on a string of lottery tickets win some or all of it back, they generally decide to keep trying their luck instead of quitting. The technical way to say on the average a person will lose money in the lottery is to say that the expected value of playing the lottery is negative. So here is a definition. Suppose the possible outcomes of an experiment or random process are real numbers, A1, A2, A3, ... all the way up to AN, which occur with probabilities P1, P2, P3, all the way up to Pn, respectively. The expected value of the process is the summation of k equal 1 to n. We take the payoff times the probability of the payoff, and we get this sum. Now this is a definition, nothing to prove. So we're saying, oh, there's a chance of getting this payoff, so you multiply by that probability, and so on until you exhaust all the probabilities associated with the outcomes. So let's compute the expected value of a lottery using that definition. So suppose that 500,000 people, 500,000 people, pay $5 each to play in a lottery game with the following prizes. There's one grand prize of $1 million, 10 second place prizes of 1,000 each, 1,000 third prizes of 500 each, and 10,000 fourth prizes of $10 each. What is the expected value of the ticket? Well, each of these has the same chance of winning as any other, and so the probability of winning for any of those is 1 over 500,000 because we select 1. So we let A sub I be the net gain for the individual ticket, A sub I. So A sub I is, since the tickets cost $5 to play, the net gain is 999,995. That's the net gain. It's $1 million minus $5 for playing to play the game. So you could get back, and each of these numbers is going to be, now that's for the first ticket. For the next 10 tickets, it's going to be this. The net gain for each of the 10 second price tickets, this is that, because everybody paid $5 to play, and so on. So the expected value of a ticket then is the summation from k equal 1 to 500,000, ak p sub k, each of the P sub k's is 1 over 500,000, so we're multiplying each one of those by the winning, which is the summation of A, K, where you go from 1 to N. Now, many of these are losing tickets, and all the ones that will lose will be, you will lose this much, but some will win. And so this is 1 over 500,000, and the first place winner gets this, the 10-second place winners get this, and so on and so forth. But we come down to here, this is minus 5 times that number. So we do the calculation. We get some of these are positive numbers, but we're subtracting off a large negative number, and so we get minus 1.78 cents. In other words, the person who continues to play this lottery for a very long time will maybe win some money occasionally, but on average will lose $1.78 per ticket. This is often a kind of problem that is on the exam, so make sure you understand this. There's also a very famous problem in probability theory called gambler's ruin. Now, unfortunately, the proof that I'm going to present here relies on something I haven't covered yet, so we're going to return and prove this later when we cover that section. But we can talk about the general outcome now. So a gambler repeatedly bets $1 that a coin will come up heads when tossed. Each time it comes up heads, the gambler wins $1. Each time it comes up tails, he loses $1. The gambler will quit playing either when he is ruined, loses all his money, or when he has M dollars, where M is a positive number he has decided in advance. That is capital M. So if we let P sub N be the probability that the gambler is ruined if he begins playing with N dollars, and if the coin is fair, we end up having an equation that we can show, and this is actually the expected value. And so this is going to be, it is 1/2 PK plus 1/2 PK minus 2. This follows from the fact that if the gambler has K minus $1, then he has an equal chance of winning $1 or losing $1 on the next play. If he wins $1, then his chances of being ruined is PK, whereas if he loses $1, then his chance of being ruined is PK minus 2. And both of those are equally likely. And P0 is equal to 1 because if he has $0, he is ruined, and PM is equal to 0. Because once he has M dollars, he quits, and so stands no chance of being ruined. So P0 is 1, and PM is equal to 0. And we're to find an explicit formula for P sub N. Again, the proof of this is something that I'm not prepared to go over with you today because it relies on something that we haven't covered, but the conclusion is interesting. The larger capital M is relative to N, and that means the closer P sub M is to 1, the larger amount of money the gambler sets himself as a target, the more likely he will go broke. Conversely, the more modest is his goal, the more likely it is to reach it. Maybe stands to reason, but we have a mathematical proof that we will do someday soon. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now more than ever, take care of yourself and of each other. God bless you all.